this is a review of properties of exponents. And what I want to make sure is we understand kind of the difference really between problem 1 and problem 2. The nice thing is we are going to keep reviewing these skills over and over again as they come up. What we're going to look at here is the first skill. If you're going to look at just the real numbers, you're going to multiply those together and get negative 15. And then we want to think of, well, what does it mean? Let me recalibrate. This has been bugging me all day. Okay. There we go. Okay, and then think about what does it mean to have x to the third power? It means x times x times x. And what does it mean to have x squared? X times x. So how many x's would be multiplied together? That would be x to the fifth power. So my rule is when you're multiplying, a faster way to do that is just add the exponents together. 3 plus 5 gives me, or 3 plus 2 gives me x to the fifth. But what about if I have a problem like number 2, where I have a power to a power? First off, it's almost like you're raising each piece to a separate power. And by the way, I'm showing way too much work for all this. My goal is just to help you review, okay? So, now let's think of what all this means. We know what 3 to the third power is, that's 27. But what does x squared to the third power mean? It means x squared times x squared times x squared. Well, using the same logic we did up here, if I take 2 plus 2 plus 2, that gives me 6. So a faster way of doing this is that if it's a power to a power, you would multiply 2 times 3 to get 6. Okay? So hopefully this is some good feedback, just review of Algebra 1 material. Number 3 is testing really one big thing. It's not technically this 4, but we would distribute the 4. So that usually most kids are pretty good with. What it's really testing is this subtraction. We don't like to think of it as subtraction. We want to think of it as adding the opposite. So I'm going to change this to addition, but that would change every sign to the opposite sign. Or another way to think of it is you're really distributing a negative 1. So this becomes a negative 1a and a positive 8. And now we're just going to add our like terms together. So then I get negative 20a plus negative a, so I have negative 21a, and 24 plus 8 is 32. Usually the error occurs, and maybe some of you just noticed it, is with the negative. Forgetting about everything in that sign is opposite. Okay? That's a big part of what we're doing today. All right, number 4, I like to think of this as 2 different ways, 2 different problems. I like to think of it as a fraction, or 16ths. We can reduce that down. 4 over 16 is the same as 1/4. Now, what about the m's? Okay, I definitely would not expect this word, and I really don't want to see it, but what is it? M to the 7th power is m times itself 7 times over m to the 3rd power. And then we have common factors, right? An m on top and an m on bottom. So they reduce out, and all that's left is the m's that are on top. Well, a faster way of doing that is to subtract these exponents. 7 minus 3 tells me that I have 4 m's left over, and they're in the numerator. Now, you could write it that way, or you don't have to write the coefficient of 1. Because 1 times anything is 1, is itself, so you're good there. This is most likely the way it will be written. Just a quick little side note. What if it was almost the same, except for I flipped around the 7 and 3? It would still be 1/4, we would still have 4 extra m's left over, but this time they'd be in the denominator. So just, that's a little side note right there. Okay. We will review more of this, but it'll come up in our everyday practice. We just want you to become really good at it. Quote today, the great things in this world is not so much that where you're standing, but in what direction you are moving. Okay, so we're going to start with vocabulary. If you've mastered this vocabulary, you don't have to write it down. It all depends on where you're comfortable with. Now, we've learned this before, so it's nothing brand new. But we're going to start defining 2 different terms. The first one is monomial. Notice how I wrote that. What does mono mean? 1, right? 1 single term. Now, when we talk about that in terms of math, that term could be a number, it could be a variable, or it could be a product of numbers and variables. So this is, when I talk about a number, let's say 16, right? 16 is a number, or a variable, let's call it n. Or it could be a product of those two, and actually it could be n squared, right? Or it could be the product, which means 16 n squared. All of those are examples of monomial terms. If I wanted to, I could come up with another one. Negative 3 halves x squared y to the 7th. That's an example of a monomial term. Okay. So, if monomial is 1 term, poly means, what does poly mean to you? More than 1, right? Many terms. And in this case, it's the sum of a bunch of monomial terms put together. So it could look really nice and friendly, kind of like this. There's a quadratic. That's what we just finished in the last unit. We called it a trinomial or a quadratic, but it's really a polynomial because it's got 3 different terms added together. Okay? But it doesn't have to be that friendly. It could be really nasty. We could have 17 n to the 4th, m to the 5th, plus 32 n to the 3rd, m to the 2nd, plus 17 n plus 16. Again, that's just a sum of 1, 2, 3, 4 different terms added together. Okay, so when we talk about monomial, just think of an individual term. When we talk about polynomial, it's the sum of all those terms added together. Okay. So this part here, we're going to use these 2 examples to point out some, let me make this just a little bigger, to point out some of the vocabulary. And you hopefully are familiar with these because we used a handful of them in the past. So, when I talk about the degree, if I have a polynomial, both of these are polynomials, we want to look at the degree. The degree is the highest exponent in the whole thing. So in this case, the degree of this polynomial would be 4. It's a 4th degree polynomial. The degree here would be 3. So simply put, your degree is your highest exponent. Whatever's the largest number, that's what it is. The leading coefficient is tied to the degree, and that's important for you to understand. So, if I know what the degree is, the leading coefficient is the number out in front. It's not the x, it's just the number out in front. So the leading coefficient would be 2. Now, this is a little misleading because it's not leading. A lot of times people see the word leading and think, oh, it has to be the first one. Well, in this case, this is not written in correct order. So you have two options. Leave it as is and just understand what the term leading coefficient really means, or rewrite this in the correct order. So if I rewrite it, I'll highlight it first. Here's the leading coefficient of this one. But what might be best is to rewrite this so you have your largest degree first, and then we write it in order, the next largest, and then the next, and the next. And in the past, we've called that standard form for quadratics. But here you can see now it is the leading coefficient. So what is leading coefficient? It's the number attached to the degree. And when I say degree, it's referring to the leading, the highest degree. Now, constant term. Well, let's think of that word constant. Constant means it's never going to change. It's consistently going to be the same every single time. Well, for each one of these terms, if there's a number plugged in, the only part that's not going to change is the one that doesn't have the x. So 1 is consistently 1 every time. In this case, 12, or this 12, is consistently 12. So this is the number without a variable. However you want to think of it. I'm going to still make reference to those, but I just need to scoot them down here so we can see the rest of them. So how do we name polynomials? They have some special names. Sometimes we name them by degrees, or sometimes we name them by the number of terms that they have. So I might, let's see if we can break this out. Think of this as like a chart. So if I name this by the degree, this would be considered a fourth degree polynomial. Okay. Now, it can also be called, because it's the fourth degree, it can be called a quartic function. Let's look at this one. This one would be considered a third degree. Because it's a third degree, that would be called a cubic function. But then it says it can be also classified by the number of terms. So when we talk about the number of terms, we just want to look at, well, how many terms are there? There's 3 of them. So this would be considered a trinomial. Tri meaning 3 terms. Okay. And we usually don't go higher than a trinomial. We have monomial, binomial, trinomial, and then everything after that we just consider a polynomial. So this one has 4 terms. And there's probably a name for it. I mean, everything has a name. In this case, we're just going to call it a polynomial. Our goal is to not have you just memorize a whole bunch of things that aren't really going to help you progress in what we're doing. I do want to point out one thing here. Let's say I have x squared minus 4. Okay, this has a degree 2, so this would be a second degree polynomial, but that is a quadratic. That's what we just finished studying. So we know its graph is a parabola. It's going to open up or down, and eventually we'll get into, you're going to know something about the graph of a quartic and the graph of a cubic just from what the graph looks like. Okay? And then how many terms does this have? This has 2 terms, so it would be considered a binomial. Bi meaning 2. Now, I did put a little note down here, just for us to be aware of, is when we write polynomials, it needs to be written in the format that was mentioned above, where we can identify all those elements. If it's not, we cannot have any negatives in the exponent, any roots, or any imaginary numbers. I'm just going to show you quickly what I mean by that. So, an example of what we'll call a non-polynomial would be something like this. 3x to the 4th plus, now so far that looks okay, right? 7x to the negative 2 plus 8. That negative 2 throws everything off, and it's no longer a polynomial because of that exponent. And we could come up with a bunch of other examples. Let's look at one that has a root. Okay. Now if I have 3x to the, actually that one's a little tricky, I don't want that one. 3x to the, let's say, square root of 3 plus 4. Well, that's not a positive whole number. You can only have positive whole numbers in the exponent. So therefore, that is not a polynomial. Another way to write something like that, and we're going to get into this a little bit later, is, let's say I've got a 3/4. Right? 3/4 is a way to write a root, but we haven't studied that a lot. So I just want you to know, if it's not a positive whole number, then it's not a polynomial. Okay? And then imaginary numbers, if you have like 3i somewhere in there, okay, or for some reason I want to use 7. Okay, those are examples where the 2i or even that constant with an I out there, that changes things. So we can't have those as polynomials. Okay, good news is we're not going to focus a ton on if it is or isn't a polynomial, or we are going to talk a little bit about degree, leading coefficient, and constant term, and I'll actually show you a question here. Don't write this. I just want to show you this is what delta math is going to look like, one of your pieces tonight. It's going to give you an expression. It may or may not be written in the correct order. You can see that the highest degree is written first, but then it's not written in the correct order. So just keep that in mind. It's going to ask you with a drop-down menu, what type of function is this? Now, it might say how many terms. So here we've got 4 terms. So this would be like a 4th degree or a 4-term polynomial. Or I think what they're mostly going to focus on is if it's a 4th degree, this is a quartic. And then once you put that in there, it's going to program all this. So it's a quartic polynomial with how many terms? Well, how many total terms do we have? 1, 2, 3, 4. 4 terms. The constant term is -1. This is where you got to be a little bit careful. It says the leading term. Well, if I was to write this in the correct order, what would the leading term be? It would be the term with the highest degree. So think of that as your leading term. I haven't used that lingo a lot. It just popped up on Delta Math. And then the last one, what is the leading coefficient? Well, if the leading term is 3x to the 4th, the leading coefficient is just the number that's in front. So filling in the blanks, you might take you 1 or 2 tries before you get it perfect, and then it'll be really quick. Okay, what I'd like you guys to do is see what you remember about arithmetic with polynomials. How do we add and subtract them? There's a rule that if you remember how to add or how to subtract, we kind of did this in the warm-up, so I think you'll be okay. But I want you to try number 1, and then if you're really good, try number 2. And we'll give you a minute or 2 on this. All right, let's take a look here. So first thing is when you're adding algebraic expressions, the rule is just to add like terms. What do items have in common? So I always start with the highest degree. So I'm going to start with the ones that have the third power, and it's addition. So 3m cubed plus 4m cubed. Well, that means I have 7m cubed. Notice how the exponent didn't change. It's kind of like if I have 3 apples and 4 apples, they're still apples, right? We're still adding the like terms together. And then we're going to deal with the next highest piece, which is the squared. I don't have any other squared values, so that's going to remain unchanged. And then I have to deal with the m's, and you can always call that a 1m plus 7m. And then the only thing that's left over is the constant term, and that's as far as we can go. Now, that's usually pretty friendly. It's number 2 that can be a little bit tricky. And this is very similar to the warm-up we did, that you want to make sure if you have subtraction, that's really like changing this. So my rule, I think, when I subtract algebraic expressions is we want to change the problem to adding the opposite. So there's multiple ways to do this. In terms of some people, if you've ever learned stop, chop, chop, or keep, flip, change, I just like to really, the mathematical process behind it is it's like we're distributing a -1. So what we would do is we would change this to addition by distributing a -1, and what does that do? It changes the sign value of everything in the parenthesis that comes after the subtraction sign. And now, because we changed it, we're adding, so we follow the same rule as above. Add your like terms. Here we're going to deal with the cubes first. So I have 1n cubed. Then we'll deal with the n terms. And that is as far as we can go. All right. So adding and subtracting are kind of smaller pieces of what we're doing today. They're important, but the big part of what we're doing today is multiply. How do we multiply expressions? How do we multiply polynomials? I don't want you to write this. I just wanted to show it to you in case it comes up. There's something called the vertical method, which is still addition. But what it does is it aligns your like terms in a vertical row, or rows. So notice the 1t squared, those are matched up, so I can quickly add those together. Here are the t values, remember that's a 1. Those are lined up nicely, and same thing here. So it's really convenient if it's written that way. However, it takes a lot of work just to write it that way. Why waste the time? Okay. Just for fun, why don't you try number 2? Just so I know you guys are ready to go. All right, so let's take a look. you could definitely do this in way less steps. I just try to show as much as I can. The one thing I wanted to show you with a problem like this is it's not written in a very friendly order. So when you're gathering your like terms, do this with certain purpose, and let's start with the highest degrees first. So now I've got 9 plus -1 is 8 d to the third. And then go to your next highest terms, which is the 13 d squared. And then we've got the next term, which is 8d. And the final terms are the constants, which is +1. And that way, you can identify what is the degree, it's 3, what's the leading coefficient, it's 8, and what's the constant term, it's 1. So, just as you're doing it, have some purpose and intent and practice writing it in correct form, like that. Okay. Now, I don't want you to write this. This is just giving you guys an idea. We are going to do multiplication of polynomials. And remember, how do we multiply? We're going to multiply each term of the first polynomial by every term of the second. That's kind of like FOIL, right? But FOIL was a binomial times a binomial. What happens if there's more? We still use the idea of FOIL, but it doesn't fit the acronym. So there's 3 methods that we would like to do. And I'm going to say, hopefully you don't choose vertical. That's like doing the long multiplication where you carry the 1 and then carry the 2. And we're not going to do that, but it's an option. We're going to show you how to do the arrows method, which is like FOIL. And what I hope you choose is the box method. I like that because it's easier to check your answers. So we're going to do a couple together, and I want to purposely do this kind of modeling how I would show the work here. So let's do these one by one together. And let's start with this one right here. Now I will mention that there's a special pattern here that you might know the answer to. Okay? Kyle, let's put that away. Okay. So you might know the answer to this without doing any work. And that actually is the goal, to recognize special patterns. But if you don't get it this year even, you're fine. Okay? So let's do the arrow method with this one. When we multiply, 5 times 5 is 25a squared. And then I'm going to do the outside terms. 5a times 1 is 5a. And then I'll do the inner terms. That's the I in the word FOIL. And then I'll do the last 2 terms, which is -1. Now, with this method, you're not done because you do have like terms that you need to combine. Okay? And you'll notice something very special. This is part of the pattern. What happens to those like terms? They add up to 0. They're gone. Right? So what's left over is 25a squared minus 1. Now, because of the way that this is set up, these are called conjugates, which we'll explore a little bit later. But conjugates are when you have a number, 5a minus 1, and you have almost the exact same 5a plus 1. So when it's the same number and they differ by a negative and a positive, they will always have your middle like terms reducing out, and you could go from here right to here without showing any work, if you recognize the pattern. If you don't recognize the patterns that we talk about today, then you're okay. Okay, then you don't have to do it the shorthand. Now, you could do FOIL here. Don't write this one, but watch what would happen. I would have to do this, this, and this. So I'd have to have negative y squared times all those. And then I'd have to multiply all of that. And then I still have to bring this 1 to each piece. That's a lot, right? There's a lot of chances for error. You'll have 9 different terms here that you'll have to group together. So, I don't think, even though it's possible, I don't think this method is great for the arrows. I would prefer, and this is just my own preference, to do the area model. So I would like you guys to write this one. I have a trinomial times a trinomial. 3 times 3, which is 9. That's why there's 9 boxes. And what we're going to do is pick one of the trinomials to go across the top, and the other one can go across the left side, down the left side. And then our job is to multiply all those together and fill in every box. And you'll notice something with the like terms, which is why I like this method. If I multiply carefully, y squared times negative y squared is negative y to the 4th. And then I usually take this y squared and I go right across. So y squared times 4y is positive 4y to the 3rd. Remember there's a 1 there and we add our exponents. And then y squared times 1 is positive 1 y squared. And then why don't you guys go ahead and finish this problem as far as you can go. All right. Assuming I didn't make any mistakes, which last hour I did, and I'm actually glad I made that mistake last hour because it proved why this method is probably more preferred. I forgot a squared right here. So I made a mistake, and one of the students very quickly, hey, Straub, you missed this? And we identified it quickly, and that's the benefit of using this model, is you can identify if you make a mistake very quickly in it. Okay, now notice, I tried to write these with a purpose in terms of the color. And you don't have to use different colors to do this, but you'll notice why I did that. What do you notice about all the different colors? They have the same exponent, right? If it's the same color, then they have the same degree, so they're like terms. So when writing your answer, you want to write this in correct order. You want the highest degree to come first. And then you're going to take your 2 red terms that are the thirds, and you're going to add those together. And then you're going to take your blue terms, which are also like terms. You get negative 35 plus 1, which is negative 34 y squared. And then I've got my terms written in black, which is 4y. And then we've got our constant term, that is 3. Okay. So, you get to choose. If you think foiling or the arrow method is going to be better, go ahead and use it. I'm not going to force you to use one way or the other. I'll encourage certain ways, but whatever works best for you. Okay, so now we're going to look at just some things that come up that may have some special patterns to them. And I definitely would write these 2 down. We're going to do this one first. So the first thing I'm going to ask you is think about what this is. A lot of students make errors on this problem because they see the thirds and they think, oh, I can just take this to the third power and this to the third power. And they get two separate answers and they think it's subtracting and they think they're done. That's not the case. You got to think of what does it mean to have something raised to the third power? It means it's multiplying by itself 3 times. So my advice is to write out what raising something to the third power means. Multiplying whatever's in the parentheses by itself 3 times. Now, we have to expand this out. We have to multiply and we can't do it all at once. So here's my advice. I like FOIL when I have a binomial times a binomial. So let's FOIL the first 2 parentheses and leave that third one alone for right now. 3w times 3w is 9w squared. 3w times negative 2 is negative 6w. And then we're going to bring the negative 2 to the other 2 terms. So that'll give me another negative 6w and a plus 4. And then we do have the like terms. But we did not do anything with that third parentheses. So that third parentheses is there until we officially need to use it. And now this problem turns into something just like the problem we did before. I've got a trinomial, 3 terms, times a binomial. So you could do FOIL here if you want. But to be honest, I really prefer to use the box method. We'll do our trinomial up top and our binomial on the left-hand side, and then it's fill in the boxes, and I'll let you guys finish this one. And then you should end with 27w to the third power minus 54w squared plus 36w minus 8. Now, there is a special pattern to this that if you recognize it, you could go from the original written expression all the way to the answer and skip all this work. I'm not going to teach it to you because it's a lot. It's not, in my mind, right now, it's not worth us learning at this moment. But we are going to show you one of the patterns that you might be able to use in this next example. So let's write this one down. I believe this is the last problem. Oh, sorry. I don't know what happened there. Yeah, this is the last problem that you guys will write. If I can get back to where we were. There we go. So, I've hinted that there are special patterns that you could use. The nice thing is you can still get the answer without doing special patterns. All you got to do is do the work that we've been doing, and there you go. My thought is the more you do these, the more you'll start realizing that those patterns exist, and when you see it again, you'll be able to do it. So, let's look at a plus b squared. Now, there aren't any numbers in here other than the squared, and that just means you're doing a plus b times a plus b. Now, you can FOIL here if you want, or you can do the area model. I'm going to do the area model just down here quick. And then we'll just fill in the boxes again. A times A is a squared. A times B is a positive AB. B times A can also be written as AB. And then B squared, B times B is a positive B squared. So, what's my answer? My answer to this is A squared plus 2AB plus B squared. And that might not be anything cool right now. Why is that special? We just multiplied two things together. Well, let me show you why it's special. And I'll just hint at the pattern. What if I said, now go ahead and do x plus 2 squared. It's in the exact same format as what we have right here. Which means I get to skip all of this work and I can go right to the answer. Okay, so let me show it to you. Here's A, here's B. According to what we did generically here, I have to take A and square it. So I have to take the x value and square it. That's the first part. And then I have to do 2 times A times B, which I would do that in my head, right? 2 times x times 2. Well, that's going to give me 4x. So this is kind of what I'm doing in my head. And then the last part says take your b value, whatever that is, and square it. So you can go from here right to your final answer. It's kind of a cool little pattern that exists because of the fact that we know what algebra is. All right, really quick. You don't have to write this. What if I made it just a little harder? It's still almost the exact same format. The only difference is I have a subtraction instead of an addition. But I'm still going to do the a value, which notice this whole thing is a. So I'm going to square the a. 4 squared is 16, and then x squared. And then because it's subtraction, this would be a minus 2. So I'm going to do minus 2 times a. So negative 2 times 4 is negative 8. Times 5. So negative 8 times 5 is going to be a negative 40x. Plus, what is 5? Negative 5 times negative 5? That's how this pattern can work. Now, if you don't like that, don't use it. Right? Do it the long way, and you get the exact same answer. It honestly saves you 30 seconds, maybe. And if you're going to make an error trying to do a pattern, it's not worth it. Okay? So let me show you quickly. I don't want you to write these down because I don't want you to focus on them until you're ready to learn them yourselves. But what did we just do? We actually talked about this one in the warm-up. I'll show you quickly. Remember, no, I'm sorry, it wasn't the warm-up, it was... It was right here. So remember I threw that word conjugate out? So 5a minus 1, 5a plus 1. These are identical except for one's minus and one's plus. And remember how the middle term's reduced out? If you see that right here, notice a plus b times a minus b. You see your middle term? It's gone. That's a pattern that you can do and you can use. Okay? Here's a pattern we just discovered. A plus b squared is really the pattern a squared plus 2ab plus b squared. If it was a minus, the only thing that changed instead of a plus is a minus. How come this isn't a minus? That's a good question. Well, if I took negative b and squared it, a negative times a negative made that positive. So that's why that pattern is the way it is. And then these are ones that I'm just going to say exist. We could do the same thing with cube. So remember all that work we did with cube? It exists in the same feature as the squared values do. But you can see the patterns get pretty crazy. There's something called the Fibonacci sequence that actually is the reason why these patterns exist. And that's a really cool math connection that we're not going to explore, but if you're interested in it, you could look at it. So, like I said, these patterns are there for you to recognize. I wouldn't try to memorize them. In the years past, I've had students try to do them, and they've made so many errors that it actually hurt them in the long run. So, proceed with caution, I'll tell you that. And I will post these on the Schoology notes, so if you need them, you can go back and look at them. All right, our homework tonight is Delta Math. It's technically 5.1, but mostly 5.3 from our textbook. Remember to submit a screenshot to Schoology when you're all done. Those of you in class today, you'll be working on this when we come back in the afternoon.